Hi everyone, last example. This one's a little different. We get a formula up front, but I think in a lot of ways it's actually easier. I just wanted to make sure I worked over something like this so it didn't mix you up when you hit it. So we have an insect that's moving along the curve y equals 4 minus the square root, or I'm sorry, 4 minus x squared over 16. So this is a parabola that opens down. And let's see, so it's flipped, it's shifted up 4. So this is at 0, 4. And then what do we have to do to get it to be 0? We have to get 64. So at 8, and then it would also be a negative 8. So this is fairly wide. This is vertically compressed by 1/16 or horizontally stretched by 4, whichever way you want to think about it. So the way I'm getting this 8 just by staring at this thing is just kind of guess and check. So if I plugged in 8 in here, I get 8 squared, which is 64. 64 over 16 is 4, and 4 minus 4 is 0. So that's going to be my 0. So this is the curve that it's crawling along, and units are both directions are in feet. We are supposed to figure out when the bug passes through the point 4,3, its y-coordinate is increasing by 20 feet per second, and we're supposed to figure out how fast its x-coordinate is changing. So we already have the formula that relates the x and the y-coordinates. It's this y equals 4 minus x squared over 16. So we just need to take derivatives with respect to time. This is per second. So we're going to say dy dt is equal to, the 4 drops out, so we're going to get negative x squared over 16, so the 2 will come down in front. We'll get negative 1/8 x, and then we'll get a dx dt from our chain rule. Okay, so we know that the bug is passing through the point 4,3, so we know that x is 4. So this is negative 4 over 8, which is negative 1/2. We also know that y was increasing by 20 feet per second, so dy dt is positive 20. And if we're looking for dx dt, we just have to multiply by negative 2. So we get dx dt is equal to negative 40 feet per second. Seems like a very fast bug. Super speedy bug. Okay, so let's see, 4,3. 4, so right here. Okay, so what we're saying is if we're stuck on the curve and our y-coordinate is increasing by 20 feet per second, the only way for our y-coordinate to get bigger at this point is for us to move to the left. So our x-coordinate has to be decreasing at a rate of 40 feet per second to stay on the curve. Part B asks us how fast the y-coordinate is changing when it's passing through the point 0, 4. So we have this formula, dy dt equals negative x over 8 dx dt. We don't have to redo that. Nothing about that has changed, but the plugging in has changed. You were not given a dx dt, but you are given that x is 0 and y is 4. And notice, if you plug in x equals 0 here, you get 0. So right at the instant when it hits the vertex, its y-coordinate is not changing. And that's that same idea of like horizontal tangent line. So right there for one instant, its y-coordinate is not changing. Feet per second. Okay, and then the last part, if the x-coordinate is increasing by 25 feet per second, when it reaches the point negative 8, 0, how fast is its y-coordinate changing? So now if we go back to our dy dt equals negative x over 8. So our x is now negative 8. And then our dx dt is 25. So these minus signs will cancel out, and the 8s will cancel out. And it looks like at that point, dy dt is also going to be 25 feet per second. Okay, so let's see, where are we? We're at negative 8, 0. So that's back here where we cross the x-axis. So if our x is increasing, our y should also be increasing to stay on the curve. So that seems reasonable to me. All right, thanks for watching.